just review very briefly stuff that we did last time. And then we'll move into the new material, talk more about Grignard reagents, more reactions of alcohols, etc. We talked about simple nomenclature of alcohols. Alcohols, we said, basically have a hydroxyl group, samples of ethanol, cholesterol, beta-glucose. The OH group, very highly polar, hydrogen bonds nicely. It's responsible for virtually all the physical and chemical properties of alcohols. For nomenclature, we're going to take the parent. We're going to put an OL on the end. The alcohol is a high priority group. It will tend to be the last suffix in most names, at least the ones that we've done so far. We're going to number this thing at the end closest to the hydroxyl group. We are going to number substituents alphabetically. Look at a very simple example here. This is a new one. Let's take a look at this guy. This is a dual functionality. It's both an alkene and an alcohol. Now, as we look at this, first thing we would do is find our parent. Parent's not difficult. It's 1, 2, 3, 4, 5. We're going to start numbering on this end so that we give our alcohol the lowest number. In our name, we have to convey that we have an alkene at carbon number 3. Since this is a pent parent, we would start off just with 3-pentene as our root name. We also have stereochemistry here around the alkene that we're going to have to include. And we have to indicate that we have an alcohol here at carbon 2. Because we have two functionalities in this compound, we put the pentene first, and then we indicate where the alcohol is just by saying 2-ol. 3-pentene, 2-ol. Stereochemistry here. What is this?
Cis.
It is cis. We could put cis. We could use EZ. If we used EZ, it would be Z. Z, 3-pentene, 2-ol. Remember that we dropped the last E here on pentene. For me, that's not a really big deal. If you happen to put an E in on the exam or something, that would not be a game killer. Any questions? This is a new set of compounds. Let's name these. You don't have these on your handout. So I'll pause just a moment. On our first one here, we're going to choose a parent that's going to contain the alcohol. So this will be carbon 1, and we'll number this way. We need to convey that we have methyl groups at carbons 2 and 4, and that we have a double bond at carbon 4. We also have stereochemistry we have to worry about. Is this alkene E or Z? See, now it's not quite so easy to use cis and trans, is it? Well, the highest priority here on the terminal carbon is going to be the methyl group, obviously. This is a CH2 attached to a carbon. This is a CH3, so this is going to be the highest priority. That's going to be cis or Z. So our name is going to be, let's see, that's 1, 2, 3, 4, 5, 6. So it's a hexene, 1-ol with a 2,4-dimethyl. Z, 2,4-dimethyl, 4-hexene, 1-ol. Our next one is just so delightfully trivial. It is a cyclopropane parent. We have hydroxyl groups in carbons 1 and 2. This is going to be a 1,2-diol. We would just call it cis, because they're both coming towards you, 1,2-cyclopropane diol. And this last one is just a simple saturated alcohol. Our longest chain, well, we're going to start numbering down here so that we give our alcohol the lowest number. We have an alcohol at carbon 3, so it's a 3-ol. We have an ethyl group here at carbon number 4. And our parent is going to be 1, 2, 3, 4, 5, 6, 7. So it's a heptane, 4-ethyl, 3-heptanol. Any questions? On this exam that's coming up, we cover alkynes as functional groups. We cover alkynes and their reactions, and we cover alcohols. So make sure that you are familiar with nomenclature of simple alkenes, alkynes, and alcohols. Reasonable?
The sample exam will give us all these same ones, right?
Yeah, sort of. I hope. Got to get the thing finished. All right, we talked about simple reactions of compounds that gave alcohols. We did a whole bunch of alkene reactions last time, where we could hydrate and things like that. The new reactions in this chapter are reduction and reactions with Grignard. And we also have oxidation and other coupling reactions. Borohydride. Borohydride is a reducing agent. Basically, we're going to donate a hydride to a carbonyl compound, converts an aldehyde here into a primary alcohol. You could also do this with lithium aluminum hydride and ether. If we have a ketone, if we do the reduction, we wind up with a secondary alcohol. We can make alcohols using Grignard reagents. We'll talk about those today in more detail. Grignard reacts with a carbonyl. In this case, this is an aldehyde, so we get a secondary alcohol. With a ketone, we get a tertiary alcohol. Aldehydes and ketones, once again, primary and secondary alcohols. Secondary, tertiary alcohols from aldehydes and ketones. Borohydride is a very nice reagent. It's easy to handle, soluble in water, all of those sorts of things. The problem is that if you have mixed functionalities, as in this case we have both an alkene and a carbonyl, we can get reduction of either or both. Here we wind up with roughly 50-50 mixture of the alcohol from the reduction, and here we have the alcohol and also the reduction of the alkene. Lithium aluminum hydride is much more selective. Here we wind up with virtually quantitative yield of the desired compound and just a trace of the over reduction. Lithium, however, as we pointed out last time, is a little bit dangerous to use. You'll never use it in the routine undergraduate lab. The mechanism of the lithium reduction and the boron hydride, frankly, all we're going to do is donate a hydride. Now just remember, this is going to be a hydrogen with its pair of electrons, H minus. H minus is our nucleophile. The carbonyl carbon is the electrophile. Remember, it's partially positive because it's bonded to the electronegative oxygen. H minus is transferred. We wind up with this addition intermediate. If we take and we quench this with acid, we wind up with the alcohol. Lithium is a very powerful reducing agent. It can react with lots and lots of different functionalities. We haven't had many of these. Epoxides, aldehydes and ketones, like we just said. We're going to look at esters right now because it's kind of a neat reaction. Same sort of thing happens with carboxylic acids. Reaction with azides and nitriles, we'll have to wait until next semester. But it's a very, very powerful, very versatile reducing agent. Reaction with esters. This is actually fairly predictable. And I want you to be able to understand these types of reactions and their predictability. What we're going to do here is take lithium, we're going to add our hydride to our carbonyl carbon. Now when we do this, we're going to get our addition intermediate. We've seen that before. With the alcohol, it's just a simple O minus. So the first step of the reaction would look like this. Now this intermediate differs slightly or significantly from the addition intermediate that we get just adding to an aldehyde or a ketone. The difference is this alkoxy, the OR group here, that was part of the ester, this is a leaving group. Now remember, we've talked about leaving groups in nucleophilic reactions. A leaving group in general is something that can just grab its pair of electrons and go. If this oxyanion collapses, that is, the electrons move back down, the electrons bonding the OR group, or leaving group, can depart, and we wind up with alkoxide, and we have reformed a carbonyl. So think about the logic here. We add a nucleophile, form an addition intermediate. This addition intermediate has a leaving group on it. The leaving group can grab its electrons and leave, and when it does, we reform a carbonyl. Now that's kind of neat. When you get to 235, you will do lots and lots of condensation reactions. Condensation reactions occur between aldehydes and ketones. Those will all involve addition intermediates like this with a leaving group. So it's a very important concept to get down. All right, but in this particular reaction, what have we done? We started off with the carbonyl. We added one hydride, And by gosh, we have a carbonyl again, don't we? So what is this carbonyl going to do in the presence of lithium aluminum hydride? Well, it adds another one. Now we have an addition intermediate with no leaving group. This guy is simply going to pick up a proton, and we wind up with an alcohol. So we've taken an ester, and we've converted it to a primary alcohol. We've added 2 moles of hydride. This is the same reaction that happens with a carboxylic acid, except instead of OR leaving, we have OH. So this works for both esters and carboxylic acids. Any question? It's not only a neat reaction, but it's a preview to all the condensation chemistry that's coming next semester. So make sure you get the concept of our addition intermediate with a leaving group. All right, whoops. Shoot. That product wasn't supposed to show, but it did. Sorry. All right, what you were supposed to do in this one was predict the product of this reaction. Obviously, this is the product, but let's make sure that we understand where it came from. We're starting here with a carboxylic ester, right? Our reaction conditions are simply lithium aluminum hydride. What happens here is we're going to add 2 moles of hydride to our carbonyl carbon and convert it to a primary alcohol. Remember, when we do this type of reaction, the alkoxy group, whatever is attached as our ester, is lost. It's gone forever. You never see it again. The carbonyl carbon is converted to our primary alcohol. So we lose the alkoxy from our ester. Carbonyl becomes a primary alcohol. Go ahead and look at this one. This is the natural product camphor. It's a bicyclic ring, 2 methyl groups on the bridge, another methyl group here. All we're doing here is a simple reduction with lithiol on our carbonyl. When we do that, we're going to put a hydride on here. The product's going to look something like this. I've drawn it with the hydride coming in from the bottom. Why did I do that? Well, if you look at the top here, it's pretty crowded, isn't it? Lithium aluminum hydride is large enough that it can discriminate between the backside attack here, which is fairly unhindered, and the top side attack, where it would have to get in past these methyl groups. Our final. Here we have a carboxylic acid. In our carboxylic acid, we're going to reduce it with lithium aluminum hydride. Just like an ester, we're going to add 2 moles. The OH group is going to be gone. Carbonyl is going to be converted to a primary alcohol. And we will get a product something like this. Any questions? The addition intermediate here has a leaving group. Therefore, we form another carbonyl, add another mole of hydride. The addition intermediate here also has a leaving group, OH minus. Add 2 moles of hydride and get to the primary alcohol. Any questions? On the exam, I'll probably just mix in lithyl and borhydride. Again, it's the same chemistry, simply add a hydride. We're not going to worry too much about the fact that borhydride would mess with the double bond here. So at this level, we're going to use the two interchangeably. Let's just look at a couple reactions of borhydride just to make sure that we get it. Aldehydes and ketones, again, primary alcohols. In this case, we wind up with a tertiary, secondary alcohol. Ketone, secondary alcohol. All we're doing, once again, is adding a hydride ion to the carbonyl. Then we work it up with water and acid in the second step. All that does is take the addition intermediate and convert it to the OH group. Let's go ahead and do some quick, simple problems. For these reductions, just like the product of the reaction with borhydride. Remember, all borhydride's going to do is add hydride to the carbonyl carbon. The carbonyl oxygen will wind up as an OH group. Trivial chemistry. We start with cyclohexanone. Going to add a hydride to the carbonyl carbon, convert this to an OH, and it looks like that. If we take benzaldehyde, borhydride will not mess with the benzene ring. We'll simply add the hydride to the carbonyl carbon. Oxygen becomes an OH, and we get benzyl alcohol. This is acetophenone. If we take acetophenone, a ketone, add a hydride to the carbonyl carbon, this will become an OH, and we have a secondary alcohol. Any questions on borhydride or lithium aluminum hydride? All right, let's move on to Grignards. In our last chapter, we dealt with organometallics, and we were introduced to the concept of a Grignard reagent. Organometallic reagents are very useful, very powerful in organic chemistry. If you take virtually any alkyl, aryl, or alkenyl vinyl halide, you can react it with magnesium metal. You do this in ether, you wind up with a complex reagent known as a Grignard reagent, abbreviated R for whatever group you start with, MgX, where X is the halogen that was attached. Some specific examples. Well, before we do specific examples, the point you want to remember is that when we make a Grignard reagent, the alkyl, aryl, or vinyl group is going to act as if it was a carbanion. Now we know what we're going to do with that carbanion, don't we? Just like we added hydride to carbonyls, this is going to let us add an alkyl, aryl, or vinyl group directly to a carbonyl carbon. Same chemistry. All right, specifics here. Here we have chlorocyclohexane. If we take diethyl ether, keep it cold, magnesium, we wind up with essentially quantitative yield of the cyclohexyl magnesium chloride. Carbanion, the negative charge, is going to be on this carbon, and that's the carbon that's going to be the nucleophile for our carbonyl addition reactions. We can also do this, like I said, with aryl, vinyl, whatever. This is bromobenzene. Bromobenzene, diethyl ether, have to warm it up a little bit, reacts to give phenyl magnesium bromide. Again, essentially quantitative. It's a very nice, very clean reaction. Any questions? Now we looked at the structure of the ether complexes in the last chapter. Just to review, this is methyl magnesium bromide. Methyl group, there's a magnesium, there's the bromine. This is the bare compound itself. This is the methyl magnesium bromide ether complex. If you look, you can see the two ether oxygens here and here, and they are bonded or chelated to the magnesium. Here is our original compound right here. It's gone from linear to a more or less tetrahedral geometry. Now, as it does this, we're placing electronegative oxygens here next to the magnesium, and that changes the charge distribution. If we look at methyl magnesium bromide in an electrostatic potential map, we can see the magnesium here is the Delta blue, nice red bromine, kind of a pale green methyl group. The complex, it changes somewhat. We have much more charge up here on our bromine, but the important thing is that we also have this bit of red, that is the negative charge, that's now associated with the methyl. So the ether is actually a very important component of this reaction complex. It allows the carbanion character to show, and that's what makes this reaction work. The mechanism is going to be exactly like we saw with hydride. If we take a carbonyl compound and we take virtually any Grignard reagent, the negative charge on the alkyl, aryl, or vinyl group is going to be our nucleophile attacking the carbonyl carbon. When it does, we wind up with an addition intermediate. Now you know enough to look at this and say, okay, we started here with a ketone. We've added an alkyl, aryl, or vinyl group. We have an intermediate, but no leaving group, do we? So the reaction's over. We've converted this from a ketone to a tertiary alcohol. If we take and we dump this into water, all we're going to do is protonate this and wind up with our simple tertiary alcohol. Very clean, very simple reaction. things to remember. If we take a Grignard reagent and react it with formaldehyde, a carbonyl with a hydrogen on both sides, also called methanal, that will give us a primary alcohol. If we react a Grignard with an aldehyde, we will get a secondary alcohol. If we react a Grignard with a ketone, we get a tertiary alcohol. And if we react it with an ester, we'll see we also get a tertiary alcohol. We'll look at that in a minute. We wind up with Grignards, with either primary, secondary, or tertiary alcohols. Only time you'll get a primary is with formaldehyde. All right. Very quickly, just look at this and draw me a product. We're starting with cyclohexanone. We are reacting this with methyl magnesium bromide. When you see this, it should scream at you, my methyl group is going to act as a carbanion. It's going to be my nucleophile and simply add to the carbonyl carbon. Our addition intermediate is going to look like this. We have gone from a simple ketone to this oxyanion. Our second step is to dump this stuff into water, maybe a little bit of dilute acid. When we do that, we're going to protonate the addition intermediate and write the alcohol. On an exam, if I gave you this question, and I simply said, give me the products, don't bother writing the addition intermediate, only write the final alcohol, tertiary alcohol, as our product. If I ask you to show a mechanism, however, that's when you should show the addition intermediate, anything else, and then our final product. Any questions? Let's do it again. Here we have benzaldehyde with methyl magnesium bromide. Once again, our methyl group is going to be our nucleophile. It's going to add to the carbonyl carbon. When it does, we will make an oxyanion, and it will look like this. Because this is an aldehyde, we wind up with the oxyanion of a secondary alcohol. Dumping this guy into acid or water, we wind up with alpha methyl benzyl alcohol. What would you name this guy? Okay, think about your rules. Your parent has to contain the alcohol, doesn't it? So how long is our parent chain? It's 2 carbons. 1, 2. Right? This is a phenyl substituent, right? So the phenyl group is attached to carbon 1. This would be 1-phenyl ethanol. Let's do another simple one here. Here we have phenyl magnesium bromide. We are reacting this with acetone. When you see this, you look and say, all right, the carbon here is going to be our nucleophile. It's going to pretend it's a carbanion. It's going to add to the carbonyl carbon. And we will get this oxyanion. Once we have the oxyanion, we simply dump it into dilute acid, and we wind up with the tertiary alcohol. Now, once again, I will ask you, let's name this guy. We just did it. You should be able to do it easily. Again, our parent is 2 carbons, isn't it? 1, 2. On carbon 1, we not only have our hydroxyl group, we have a phenyl and a methyl. So this would be 1 methyl, 1 phenyl, ethanol. A nice way to combine reactions and nomenclature on an exam like the one that's coming up is to put in a simple reaction like this, ask you to draw the product, and ask you to name it. Well, what is the name? It's an ethanol, isn't it? And what's attached to our ethanol? Methyl group at carbon 1, a phenyl group at carbon 1.
So you're using carbon 1, the one that's in the middle?
Yep, well, this is the one that the OH is attached to. So by definition, that must be carbon number 1. 1 methyl, 1 phenyl, ethanol. Everyone get that? No?
Yeah, you're saying, okay, you're just saying,
All
go to
right.
the carbon, even if it's in the center right there.
All right, hang on, we'll do it this way then.
The alcohol is number 1.
Can you give us examples here number that carbon?
Where's your parent? Where's your parent? The parent must contain the alcohol, right? So we have a 2-carbon parent. Correct? What's attached to carbon 1? Well, the OH group, this is carbon 1. We have a methyl group that's attached, and we have a phenyl group that's attached. So this is 1 methyl, 1 phenyl, ethanol. Make sense? Your parent must contain the hydroxyl group. This is our parent. It's a 2-carbon alcohol, that's an ethanol. And the ethanol has a methyl group in carbon 1 and a phenyl group in carbon 1. All right, let's do a full set. This is what they look like on the exam. Go ahead and quickly draw the products. A nice simple way to do this is to dream in color. If you look at your Grignard reagent and your alcohol. If the Grignard reagent is shown here in red, carbonyl compound in blue, this is our addition compound, this is the bond that you form in the reaction. Methyl group simply adds to the carbonyl carbon. This is an OH group, and this is the bond we just made. Our next one, we're going to add a phenyl group to our carbonyl carbon. This is a ketone, acetone. So we will make a tertiary alcohol. Once again, phenyl group is going to add here. Our product looks like this. This is the bond we made in our reaction. This is the carbonyl compound. This is now an OH, and we've added the phenyl to the carbonyl carbon. Our third one here, we're going to add our Grignard reagent. This is going to be an isopropyl anion. It's going to add to the carbonyl. Because we have this methyl group hanging up here, it's likely that this thing is going to come in from the bottom side. We're going to make a bond from the isopropyl carbon to the carbonyl, and this is going to be an OH. This is the compound you get. This is the bond we made. Here's our isopropyl group from our Grignard. This is the alcohol from our carbonyl. Start to think about these things in terms of being able to take them apart let's go back to that one. To take them apart and visualize the part that comes from the carbonyl compound, that's this, and the part that comes from the Grignard. It's important to do this because we're going to do synthesis involving Grignard reagents. And when we do synthesis, we want to be able to take our compound, take it apart, and decide what Grignard reagent and what carbonyl compound we need to do that reaction. Well, let's just do some more simple reactions first. Here we have acetaldehyde, 2-carbonaldehyde. It's the essence of little green acids. Reacting with bromomethane in the presence of magnesium and ether. The bromomethane is going to react to make methyl magnesium bromide. That's our Grignard reagent. The methyl group is going to add to the carbonyl carbon. The oxygen will be an OH group, and that is a simple product. Now think about it. Our hydrogen is still here, isn't it? We've gone from the aldehyde to the secondary alcohol. One methyl group from the carbonyl compound, one methyl group from our Grignard reagent. On an exam, you'll probably see reaction conditions like this. Maybe a mix, but if you see this, what you do is you look and say, bromomethane is going to react with the magnesium. That's going to make our Grignard reagent. That's going to then add to the carbonyl, work it up with acid, and we get the alcohol. Do the next one. Acetaldehyde plus bromobenzene in the presence of magnesium, followed by acid. Bromobenzene is going to react with the magnesium to make phenyl magnesium bromide. Phenyl magnesium bromide is going to add to the carbonyl carbon. This is an aldehyde, so we will get a secondary alcohol. Compound will look like this. Phenyl group we've added. Carbonyl carbon is now an OH. And here's our methyl and our hydrogen still attached. Our last one, take bromocyclohexane, magnesium. That will convert it to cyclohexane magnesium bromide. Cyclohexane carbon will be our nucleophile. It will attack acetone at the carbonyl carbon. And we will wind up with the tertiary alcohol. Aldehydes give secondary alcohols. Ketones give tertiary alcohols. Any questions? Just think about the versatility of this. Because you can make a Grignard reagent from virtually any organic halide, you can add that to virtually any carbonyl compound and make a fairly interesting set of compounds. Once we get the OH group, we can do even more chemistry on it later on. Let's go ahead and look at another way we do Grignard reactions. What if I tell you, I want you to do a synthesis here using a Grignard reaction to make this alcohol. Now there are two ways that you can do this. On an exam, I will typically ask you to show both pathways. Okay? Both pathways to make this alcohol by a Grignard reaction. Now, how do we do this? We sit back for a second, catch our breath, and we think, okay, I can do this, right? When I did my Grignard reaction, I converted my carbonyl into an OH group. Therefore, on either side of our OH are the potential places that I made my bond. So let's just start somewhere. Let's take and split this along one of the bonds adjacent to the OH group. We'll then look at what's on one side, come up with a Grignard reagent, look at the other side, and come up with a carbonyl compound. If we split here, that bond with the little red squiggle in it is the one we made in our reaction, isn't it? So, when What you need to do is ask what's on each side. This side is a phenyl group. That's going to have to come from our Grignard reagent, isn't it? And on this side is the bond attached to the oxygen. Well, that used to be a carbonyl. So now all you have to do is figure out what Grignard reagent we had and what carbonyl compound we had. The Grignard reagent was simply phenyl, magnesium bromide. We've added a phenyl group, that's all. Our carbonyl here, this is a secondary alcohol, so it was an aldehyde, wasn't it? All you do is convert the OH into a carbonyl and note that it has a hydrogen, therefore it was an aldehyde. Now that's not so tough, is it? Let's do the other side. Let's split it right here. Go ahead and draw the carbonyl compound and the Grignard reagent we needed to make this compound. Well, this time, the Grignard reagent is a 1, 2, 3, 4 carbon chunk. It was attached at carbon number 2. So this would be a butane, probably a 2-bromobutane. On this half of the molecule, this is a secondary alcohol still, so it's an aldehyde. All you do is convert the carbonyl compound here into an aldehyde. We have benzaldehyde and 2-bromobutane. Now that's simple, isn't it? That's not only simple, it's fun. Let's do it again. Take this secondary alcohol. We're going to split it. Let's split it first on this side and draw the pair. The Grignard reagent and the carbonyl compound. Split first right here. Now this is a secondary alcohol again, isn't it? So our carbonyl compound was an aldehyde. Our Grignard reagent had 2 carbons. So something like bromoethane would work. This is simply an aldehyde with a 1, 2, 3 carbon chain attached to it. And it would look like that. Bromoethane reacting with 1, 2, 3, 4. This is butanal. Magnesium converts this to ethyl magnesium bromide. Work up with acid gives us our secondary alcohol. Let's split on the other side. Going to split here. There it goes. And draw the pair. Our Grignard reagent was this 3-carbon chunk, wasn't it? Our carbonyl compound was an aldehyde with a 2-carbon chain attached. And the pair looks like this. One propane and propanal, also called propionaldehyde. Any questions? All right, let's look at this simple reaction here. What if I take methyl acetate, that is the methyl ester of acetic acid, and I react it with methyl magnesium bromide? What I wind up with is a tertiary alcohol. In this case, tert-butyl alcohol. So we've converted our ester into a tertiary alcohol by reaction with 2 moles of Grignard. Now, you already know exactly how this happens. Let's think about the mechanism. Here we have a carboxylic ester. We're going to take and react this with a Grignard reagent. Our Grignard reagent, the alkyl aryl or vinyl group, is simply going to act as a carbanion, and it's going to attack the carbonyl. Our addition intermediate looks like this. Now this should be familiar to you. If this was lithyl, and this was a hydrogen we just added, we would have an addition intermediate with a leaving group. So what happens? This is going to collapse. That means electrons move in, and the leaving group is going to grab its electrons and go. And what have we done? We have formed another carbonyl. Now, this carbonyl is sitting here in the presence of Grignard. Remember, we used 2 moles of Grignard. So what's going to happen is our second Grignard is now going to attack this carbonyl. We will get this addition intermediate, no more leaving groups, and acid will give us our tertiary alcohol. Just like in lithyl, we lose the alkoxy, it's gone forever. Forget about it. Whatever's attached to the other side survives, and we've added 2 moles of our R group to form our tertiary alcohol. The one exception to this, if this happens to be a hydrogen here, so it's a formate ester. If that's a hydrogen, then it would be a secondary alcohol. But that's the only example. Otherwise, think tertiary. Any questions? So just like lithal with an ester, you add it twice. In this case, we wind up with a tertiary alcohol as product. Now, the Grignard reaction is an amazing thing. It does, however, have certain problems. This Grignard reagent, we keep saying is carbanion, right? Because it's a carbanion, it's also a very, very strong base. And it can yank a proton off of anything. If you try to do this in the presence of carboxylic acids, amines, alcohols, here's an amine again, or an amide, this is a thiol. What it will do is simply pull off a proton, simple acid-base chemistry. Here we have methyl, magnesium, bromide, and methanol. Wind up with methane, or hydrogen off, and get the alkoxide. So, if your compound has more than one functional group, and that functional group is acidic in any way, Grignard won't work. The other limitation, if we happen to have other reactive groups, again, more than one functional group in our molecule, like nitriles, nitro groups, sulfonates and stuff like that, other carbonyls, these are going to add the Grignard as well. So if you have a complicated molecule with other functional groups or acidic groups, Grignard reactions don't work. Otherwise, they're nice and they're clean and they're happy. All right, let me show you an exam question. Typical exam question for this exam would involve a synthesis where you have a gallery of potential compounds to use. And you are asked to make one of these. Now, you can make this any way you want. But frankly, we don't have enough of a synthetic repertoire yet to do it too many ways. So we're going to have to do this using a Grignard reaction. So pretend that this was a week from today. Utilize one of these guys and make this.
Bottom left, right?
Well, do it one at a time here. What you want to do is look at it and say, what type of a compound is it? Oh, it's a secondary alcohol. How many ways do I know to make secondary alcohols? Actually, I know two. I can take a ketone and I can reduce it with either lithal or hydride. That works. Or I can make it from a Grignard reaction. As we look up top here, do we see an appropriate ketone? No, we don't. Therefore, we're going to have to do a Grignard synthesis. As we look at this, let's do our standard thing. We're going to want to split on either side, or on one side anyway, and see if we can come up with a Grignard and something else that's going to give us this compound. If we split here, because this is a secondary alcohol, we would need an aldehyde with 1, 2, 3, 4 carbons. Do we have one?
Just the one at the top.
This is the only, well, these two are the only aldehydes I see. So that doesn't work. Okay. Let's don't panic. How else could we make a secondary alcohol? Well, let's look at our potential candidates up here. If we take an ester and we add a Grignard to it, as we just saw, we can add 2 moles of our Grignard reagent and make an alcohol. If we use this guy up top here, we would lose the ethoxy group, right? But this 3-carbon chain would still survive, and that would give us a tertiary alcohol. So that one's out. However, if we use this guy, because we have a hydrogen attached, it's a formate ester, we will lose the ethoxy, but the hydrogen will be this hydrogen in our secondary alcohol. All right, so what you need to do is look at this and say what, well, I know already what carbonyl compound I want. Now I need to know what Grignard reagent I need. Let's take and split our molecule. Remember, we're going to add 2 moles of Grignard. So we're splitting here. These 2 chunks come from Grignard reagents. This part in the middle comes from our ester. So fast forward to Tuesday, very quickly, draw the structure of the Grignard reagent you need, and of course, the ester that we start with. Our Grignard reagent must have 1, 2, 3 carbons. This must be a bromine out here, or a chlorine. So this is going to be 2 moles of our bromopropane. We convert that to bromo or propyl magnesium bromide. Here is our ester. Do this reaction, adds twice, and we get our secondary alcohol. Any questions? Now, with the problem set that we're going to do after lecture today, we're going to do, maybe 4 or 5, maybe 6 of these types of problems. So we'll review these again quite thoroughly before we set out to do the exam. But this is just a standard sort of thing. You're given a selection. You have to choose one of them. If it's a Grignard reaction, here we have to split, figure out the Grignard reagent, carbonyl compound, and draw the reaction. All right, there are a couple more reactions of alcohols that we need to worry about. In addition to making Grignard reagents out of alkyl halides, we can also make alkyl lithiums. Just like a Grignard reagent, R can be virtually anything. Alkyl, aryl, or vinyl. All we do is react, say, bromobenzene with lithium, and we'll get phenolithium as our compound. Now these guys are used two ways in organic chemistry. One is as a base. If you need something that's really basic, this is essentially a carbanion, very, very basic, use it that way. Or we can add it to carbonyls. Now you already know what's going to happen here, don't you? We have an R minus, and we have a carbonyl. This is simply going to attack our carbonyl. We're going to get our addition product. When we take and dump this into acid, we've converted our ketone into a tertiary alcohol. So just like a Grignard reagent, except a little simpler perhaps, alkyl lithium, aryl, or vinyl lithium attacks carbonyl again. Aldehydes would give secondary alcohols, ketones would give tertiary. Let's look at a real example. Here we have benzaldehyde reacting with a vinyl lithium. Now I chose this one specifically because sometimes people have a real problem with a compound like this, trying to decide exactly where the anion is. Well, this is the nucleophilic carbon, right here. That's the guy that is negatively charged, right? It's the one that's attached directly to the lithium. All in the world that's going to happen is this carbon, the vinyl carbon, going to attack the carbonyl. When it does, we wind up with our addition intermediate, dump it into water, and we get the alcohol. Think backwards. All we've done is take this chunk here, the whole vinyl chunk, and we've added it to the carbonyl carbon. It's a secondary alcohol because we started off with an aldehyde. You should be saying to yourself, okay, this is just like a Grignard, isn't it? I can do Grignards, I can do this too. Let's prove it to ourselves by doing so. We have an aldehyde. We're reacting it with methyl lithium. All that's going to happen is the methyl group is going to act as a carbanion. It's going to attack the carbonyl carbon. When we dump it into acid, this is going to become an OH group. We will wind up with a secondary alcohol, 2-propanol in this case. Our next reaction, a simple Grignard reaction. We're going to take our phenyl anion. It's going to attack the carbonyl carbon. This is going to become an OH group. We will wind up with our secondary alcohol. Aldehyde, secondary alcohol. This is formaldehyde. Formaldehyde is actually widely used industrially. If you've had biology, especially in the old days, everything was preserved in formaldehyde. Now it's considered a little bit toxic, so they don't use it quite so much. Chinese also use it in wallboard, insulation, stuff like that, which is a bad thing because it leaches out. It can be somewhat toxic again. If it reacts with a Grignard, we're going to convert our Grignard into a primary alcohol. All we're doing is adding the Grignard to the carbonyl carbon. We have two hydrogens, a primary alcohol.
I heard people smoking that formaldehyde.
Um,
I've heard they dumped marijuana in there and they smoked it.
Formaldehyde, well, actually, formaldehyde doesn't really exist this way except at equilibrium. It actually exists in solution as paraformaldehyde, which is a cyclic triether, but it's in equilibrium with free formaldehyde itself. Our first one here, we have an ester. We are reacting that with excess methyl magnesium bromide, followed by workup in acid. The mistake that people make on an exam when they see this problem, they see this cyclopentanol here, and 80% of the time, cyclopentanol is somehow going to wind up in your answer. No, it's gone. You never see it again. The methyl group will, this stuff is gone. We add two methyls, and we get tert butyl alcohol. Now this next one is cute. We've made this Grignard reagent from bromoethine. That is, we took two carbon unit, triple bond with a bromine attached, reacted it with methyl or with magnesium to make the ethynyl magnesium bromide. This is our nucleophilic carbon. It will simply add to our carbonyl carbon. We have an aldehyde, so we will get a secondary alcohol, and it will look like that. Now that's kind of a cute looking reaction, isn't it? The reaction conditions here are wrong. So please forgive me for that one. I just noticed that. Here we have an alkyl lithium. It's actually a vinyl lithium. It's adding to an aldehyde. We don't need magnesium. We simply need ether in our reaction conditions. This carbon will attack the carbonyl carbon, and we will get this secondary alcohol. Any questions? You want a break? Oh, come on. We've only got about 30 more slides. Let's just try to get through this next set. All right. So far, we've talked about reactions that give us alcohols. Now we're going to talk a little bit about reactions of alcohols. Now you actually already know some of these. We know that if we take an alcohol and we add a strong acid, that we can get an alkyl halide. In fact, we did this reaction in lab. We did it under SN2 conditions. Here with a tertiary alcohol, we are very likely to form a carbocation. Again, we have to worry about rearrangement. And we know that we're going to get Markovnikov regiochemistry with respect to our halogen. Done this reaction, it's a simple thing. New chemistry. This is a very brutal, ugly reaction. Okay, brutal and ugly. There are nice ways to convert alcohols into alkyl halides. We're going to look at 3. Here's our carbocation. There's our mechanism. The first nice way is simply to take an alcohol and react it with phosphorus tribromide, PBr3. We're going to do this reaction in ether, about room temperature or so. We wind up with the alkyl bromide. The reaction is, again, very civilized. What happens is the oxygen is going to attack the phosphorus. When it does, we wind up with a phosphorus ester. Now, what we have done here is convert the OH, which is a lousy leaving group, into this phosphate ester, phosphide ester, which is a very good leaving group. And we have bromide kicking about here. Because when we do this, we remove 1 mole of bromide. What happens in our second step is that bromide is simply going to attack here. It's an SN2 reaction to give us cleanly the alkyl bromide. Now think about this SN2 reaction. What do we know about SN2 reactions? We know that attack is backside, and that if we have stereochemistry, we get inversion. So let's pretend that we had this chiral alcohol that we reacted with PBr3. We would wind up with this chiral phosphate ester. In our SN2 step, bromide's going to come in, this guy's going to leave, and we will wind up with the alkyl bromide. But because this is the highest priority group and it was forward, the bromide is now behind it, we have inversion of stereochemistry. If this is R, this is S. Things to remember. The reaction with PBr3 with a chiral compound is going to give you inversion of configuration.
You know, it looks like the methyl's in the back, and it's running into the bromine's running into the methyl. You know.
Well, no, it's got to come in opposite this group, so that's what it's meant to show. Maybe my artwork isn't perfect, but this is coming in, this is going out. Again, these two are collinear, and we wind up with inversion of configuration. We can make alkyl chlorides using a compound known as thionyl chloride, SOCl2. This is the sulfur analog of phosgene, which is mustard gas. It's not a nice compound. It's not quite as toxic as phosgene. If we do this reaction in pyridine, now what is pyridine? That's pyridine. Pyridine is a 6-membered ring, including the nitrogen. We don't know what the term aromatic means yet, because that's chapter 13, which we skipped over, haven't we? But we'll do that next semester. This is an aromatic amine. And this reaction is simply as functioning as a base or a solvent or a nucleophile. So it stinks badly, not particularly toxic, but it does smell bad. All right, so we do SOCl2 in pyridine, just like the phosphate reaction. The oxygen attacks, the chloride leaves, and we wind up with a chlorosulfide ester. Now, what do you think is going to happen next? Well, just like PBr3, chloride attacks, SN2 chemistry, and we wind up with the alkyl chloride. Again, if we have stereochemistry, we get inversion. So with either PBr3 or thionyl chloride pyridine, we can get an alkyl halide with inversion. A really, really neat thing about all this, now get excited here. The really neat thing is that if we do thionyl chloride in a nonpolar solvent, we get retention of configuration. So we can design our synthesis now to give us either inversion or retention. So we can do really neat syntheses, can't we? The way this happens, same thing is going to happen. We'll make a chlorosulfide ester. But because we are in a nonpolar solvent, we're not going to have chloride floating around to act as our nucleophile. And what happens is that this species undergoes an internal front side displacement, called an SNI reaction. Chlorine comes down, this breaks at the same time, SNI, and we get retention of configuration. So 3 things to remember. PBr3, thionyl chloride in pyridine or ether gives you inversion. If we do it in a nonpolar solvent with thionyl chloride, we get retention of configuration. Standard test question, please make sure you can distinguish the pyridine reaction and the one in pentane or something like that. All right, let's go back in history. When we were making alkenes, again, the brutal way. We said we could take an alcohol, strong acid of some sort, and simply make our alkene. We know that this reaction involves a carbocation. We can get rearrangement, and we wind up with Markovnikov regiochemistry. There is, however, a more sophisticated way to do this. If instead of strong acid, we use POCl3, again in pyridine, our friend, we wind up with alkenes via an E2 reaction, no rearrangement, nothing ugly, a nice, simple way to make alkenes from alcohols. Again, we're going to get the Zaitsev product. Mechanism. Step 1, just like we expected before, a chlorophosphate ester is going to react. It's going to form this way. Pyridine, that's our base. Simply going to pull off a hydrogen. We're going to do a standard E2 reaction to get the alkene. Zaitsev rule, no rearrangement, nice, simple, and happy. All right, 2 more types of reactions we need to deal with, and then we can take our break. Step 1. Oxidation reactions. After we go through lots of trouble and we make an alcohol somehow, what if we want to do more chemistry to it? Well, we know lots of things to do to carbonyls. Turns out that we can convert an alcohol back into a carbonyl by simple oxidation. Now there are going to be 2 reagents that we need to worry about. One we can simply call PCC, because nobody here can say pyridinium chlorochromate.
Pyridinium chloro.
All it is CrO3, that's our active oxidizing agent. The neat thing about PCC is that it's a mild oxidant. You can convert something like a primary alcohol to an aldehyde. If we simply had CrO3 by itself, it doesn't quite work. Alcohols go to carbonyl compounds or carboxylic acids. We did the previous one here with this. If we had used CrO3, it would oxidize all the way to the carboxylic acid. Therefore, if you want to stop at the aldehyde, you simply remember PCC. If you want to go all the way to the acid, CrO3, secondary alcohols to ketones, either one works. One last very specific reaction, however, is such a neat reaction, we have to look at it. This is an allylic alcohol. Remember we talked about allylic positions? Allylic is the carbon adjacent to a double bond. We talked about those with radicals, stable radicals. Well, this is an allylic alcohol. Allylic alcohols, as you'll see when you do chapter 14, which is conjugated systems. Allylic alcohol, allylic centers are what's termed conjugated, and they are very, very stable. Therefore, very easy to oxidize this to the corresponding aldehyde. It's just something like MnO2 and pentane works. MnO2, you saw that when we did potassium permanganate with an alkene. Remember the brown gunk that fell out? That was MnO2. Very mild reagent. All right, now we will finally take our break. When we come back, we'll do a couple pages of reactions, and then we will do this handout. So please grab a copy of the handout and enjoy your break.
Dr. Young, did you already check organic 2? Did you already check the organic 2 that it's already, you looked into it already? Is that why you're just skipping around chapters? Or
No, I'm not.
Okay.